Hello, this is Dr. Strickland. In this video, we will finish up our investigation of isomers with more than one asymmetric carbon. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So this is a cyclic example, and the skills involved in evaluating the stereoisomers of a substituted cycloalkane are very similar to the ones that we used with an acyclic compound. And remember that acyclic just means there's no cyclic structure in the molecule. So we're going to work with 1-chloro-3-ethyl cyclohexane. And so the first thing I did was to draw the skeletal structure. And you remember that there's a way to predict the maximum number of stereoisomers from the number of asymmetric carbons in the compound, so we've got to look for them. So any carbon of the ring that already has one substituent attached is a potential suspect. So, there's a hydrogen assumed there, and that gives us 1, 2, 3, 4 different things attached to this asymmetric carbon because the paths around the ring are different. So that's an asymmetric carbon. And similarly, we've got one right here at carbon 3. So two asymmetric carbons, the maximum number of stereoisomers can be calculated as long as you know the number of asymmetric carbons. So the number of asymmetric carbons is the exponent, and that gives us a possible 4. Now, it won't always have the maximum number, but that's as high as it can get. So in order to catalog all of the stereoisomers that are possible, we got to start somewhere. And so what I decided to do was to set up 4 different boxes that have structures that will correspond to the 4 different stereoisomers. Now you see I've got 2 structures in this first box, and that's so that we can do a really careful analysis of the configuration at carbon 1 and at carbon 3. So we'll do carbon 1 in this drawing and carbon 3 in a separate one. And then once we've got that, everything else is relative to what we've done in the first one. So I decided to put the hydrogen on the up bond and the chlorine on the down bond on carbon 1, and the ethyl on the up bond and the hydrogen on the down bond of carbon 3. So I'm going to go ahead and do that twice because these are just 2 different drawings of the same stereoisomer that we're working with here in this first box. So if we look at what we've got at carbon 1, these are the 4 things. And remember that when we prioritize those, we're going by the atomic number of the atoms that are directly attached to this asymmetric carbon. So that makes chlorine first. And then the 2 carbons will be second and third, and the hydrogen will be last. All right, and so then to determine which of these 2 paths has the higher priority, we've got to look at what's attached to the next carbon moving away from the asymmetric carbon. And then what is this one attached to moving away? So it's attached to a carbon and the 2 hydrogens that are assumed. So carbon, hydrogen, hydrogen. And then over here, this carbon is bonded to a carbon and the 2 hydrogens that are not written. So we don't have any difference yet. So if we go to the next one in both directions, this guy is attached to a carbon, and a hydrogen. And then this one, moving away, is attached to a carbon and 2 hydrogens. So we've got our first point of difference right there at the second position. And that makes this direction B and this one C. So what have we got? For carbon 1, we've got A to B to C. That's clockwise with the group of lowest priority pointing out. And that's an S configuration. All right, so we know at carbon 1, we've got the S configuration, the way we've drawn it. So we're just going to pop that in there. So we'll go down here, and now we're going to look at carbon 3. The 4 things that are attached are here, 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 and here. All right, so you can see that this one is going to be the lowest priority because the other 3 are carbons. So we've got to take a look at here, and here, and here. And this is a ring carbon, so it's a carbon and 2 hydrogens. So is this one, and so is this one, actually. So there's no difference in priority yet. So I'm going to go to the next one, which would be here, and here, and here. All right, so this one, moving away from the asymmetric carbon that we're investigating, has a chlorine, a carbon, and a hydrogen. This one is 3 hydrogens. And this one is a carbon and the 2 hydrogens that aren't shown. All right, and so now, if you look at the first positions, they're all different. And so this one is higher than that one, which is higher than that one, which makes this direction A, and then this direction B, and then the ethyl group gets to be C. So we've got, for C3, we've got A to B to C as counterclockwise, with the group of lowest priority pointing back. And that's also S. Okay. 1S, 3S is what we've determined for the stereochemistry of this stereoisomer. Now, if I want to draw the enantiomer of compound 1, how is it an enantiomer related to the original compound? All right, so you can do it first in the name, because with an enantiomer, it has to have the opposite configuration at every asymmetric carbon. So we're going to change the S to R at carbon 1 and the S to R at carbon 3. So that's how we do it in the name. How do we do it on the drawing? Well, at any 3-dimensional sp3 carbon, you can change the configuration from R to S just by switching the places of the 2 things that are attached to the ring. So here, hydrogen has the up bond and chlorine has the down bond. So if I want to change them, so chlorine would have the up bond now, and hydrogen would have the down bond. And over here, the same sort of thing. The ethyl group would have the down bond. The hydrogen would have the up bond. All right. Now, when we want to look at for the 2 diastereomers, we need to know what diastereomers are. And diastereomers, remember, are stereoisomers that have at least 2 asymmetric carbons, and you have to have at least one that has the same configuration as your reference compound, and at least one that has the opposite configuration as your reference compound. And so, since there are 2 asymmetric carbons, there are 2 diastereomers. So we can keep it the same here and switch this one. So 1s3r, or we can do 1r3s. All right. So what I want you to do is pause the video and draw where things need to be attached to this cyclohexane to make 1s3r, 1-chloro-3-ethyl cyclohexane, and then the 1r3s stereoisomer. Pause the video and do those and come on back. All right, welcome back. So wherever it's the same as carbon 1, you just draw it the same. And wherever it's opposite, then you draw them opposite. So that gives us one of them. And then over here, it's opposite on the first one. And then it's the same on the second one. And now we've cataloged all of the possible stereoisomers for this particular connectivity. All right, so that's the basic story on cyclic examples of compounds that have more than one asymmetric carbon. If you have any questions, please send them to me.